Welcome to Next Gen Manufacturing, where we dig into the incredible science behind how we build our world. Today, we're talking about what makes our most advanced materials just so unbelievably strong.
Have you ever looked up at a massive wind turbine, its blades just slicing through the air, and thought to yourself, how does that thing not just snap in half? Or a modern jet, how does it handle those insane pressures and temperature swings, day in and day out? Well, it all comes down to materials science, but the answer? It's probably not what you're thinking.
Because the real secret to all that colossal strength, it's not just about the big stuff you can see. It's hidden away at a microscopic level, in a tiny, tiny space that makes all the difference between a material that works and one that just catastrophically fails.
So to get there, we have to talk about composites. These are the real wonder materials of our time. They're engineered to be way stronger and lighter than regular old metals. But they've got this one potential weak spot, a little conundrum that engineers have been trying to solve for decades. Think of it like a cocktail. You take these incredibly strong, stiff fibers, like carbon or glass, and you embed them in this sort of polymer glue, which we call a matrix. The fibers bring all the raw strength, and the matrix holds it all together and gives it its shape. Simple, right? Well, not so fast. Okay, so let's dive into this, because the real magic, the absolute unsung hero in every single composite material, happens right where those two things meet. It's something we like to call the microscopic handshake. Now, this handshake has a proper name. It's called the interface. And it's not just some passive boundary line. No. It is an active, engineered zone. Its entire job is to make sure that when a force hits that material, the stress gets passed smoothly from the kind of weak matrix to the super strong fibers. If that transfer doesn't work perfectly, the material is pretty much useless.
Here's the best way to think about it. Imagine building a brick wall. You can have the strongest bricks on the planet, but if you use weak, crumbly mortar, that wall is coming down at the first sign of trouble. The interface is the mortar for composites. A weak interface, a weak handshake, and the whole thing falls apart. But a strong interface? That creates one solid structure that's way stronger than its individual parts.
Right, so this perfect bond, this super strong mortar, it doesn't just happen on its own. Scientists actually have to meticulously engineer the surface of the fibers. They use all sorts of chemical coatings and treatments to create the strongest possible handshake with the matrix. It's all by design. And look at the real-world data here. It's pretty amazing. This is a common glass fiber composite. Without any special treatment at the interface, its tensile strength is about 56 megapascals. But then you add just a tiny amount of a chemical coupling agent, a little something designed just to improve that handshake. And boom, the strength jumps to 69 megapascals. That is a 22% improvement from one single microscopic tweak.
But of course, it gets a little tricky. In material science, there's almost always a trade-off. As this quote gets at, when you make something stronger, more resistant to being pulled apart, you can often make it more brittle or less tough, so it can't absorb as much impact without cracking.
And that's the whole game, finding that perfect sweet spot. This chart shows that by strengthening the interface, you can literally double the material's shear strength. That's a huge win, but you might lose about a quarter of its toughness in the process. So the real goal of next-gen manufacturing isn't just to max out one thing. It's to dial in the absolute perfect balance for whatever you're building.
But a material strength on day one is only half the battle. The real test is whether it can survive the gauntlet of the real world, year after year, in all kinds of harsh, demanding conditions.
So there are two major enemies to long-term durability: aging and fatigue. Aging is basically the chemical breakdown that happens when a material is exposed to stuff like water or heat or chemicals. And fatigue is the physical exhaustion it gets from being stressed over and over again. And guess what? The interface is the first line of defense against both. Just take a look at this. This chart is showing what happens to a composite used in car parts after it's been soaked in hot engine coolant. With a standard interface, its toughness drops way down to 45. But the one with a specially engineered, water-resistant interface, it holds up way better, staying at 70. That's over 55% more durable just by protecting that tiny microscopic handshake.
Okay, so it can handle the chemical environment. What about just pure physical stress? How many times can it bend, vibrate, or get pulled on before it finally gives up? This is the whole question of fatigue life.
And the results here are, well, they're just staggering.
Under the same exact repeated stress, a composite with just a mediocre interface might fail after, say, 30,000 cycles. But if you properly engineer that interface to create a really strong, durable bond, the exact same material can handle over 1 million cycles. 1 million! We are not talking about a small improvement here. We are talking about making a product last orders of magnitude longer.
So this incredible level of control isn't just about making things better or longer lasting. It is actually unlocking the door to a much more sustainable circular economy for these amazing materials. For the longest time, one of the biggest problems with these high-performance composites, especially the kind used in planes and cars, was that they were basically impossible to recycle. It was a one-way trip to the landfill. But interface science is completely changing that game. Here's the new playbook. You take old composite parts and shred them. But, and this is the critical part, instead of just mixing those shreds into new stuff, which would be really weak, you do something brilliant. You chemically treat the surfaces of those old fibers to reactivate them. You're basically prepping them for a brand new handshake with a new matrix. And the proof is right here in the numbers. A brand new composite might have a strength of 105 MPa. If you just recycle it without any treatment, that strength plummets to 61. But by re-engineering the interface on those recycled fibers, you get back up to 85. You recover a huge chunk of that original performance. This turns what was once trash into a valuable, high-tech resource. And this exact same science is right at the heart of the next wave of green materials, biocomposites. These use natural fibers like flax. And here, engineering the interface is this really delicate dance. You need a bond that's strong enough to last the product's life, but also one that can break down when it's time for it to compost. It's all about balancing performance with true biodegradability. So it turns out the secret to our strongest materials really does lie in the smallest of places. And it teaches us this really powerful lesson for next-gen manufacturing. The future isn't just about making things stronger. It's about engineering them right down to the microscopic level to be smarter, more durable, and completely sustainable, from the moment they're made to the moment they're made again. It just makes you wonder, with this kind of control, what are we going to build next?